Hey guys, welcome to our lesson on 3.4. Today we're going to take the tools that we learned in 3.3 that we went over, those derivative rules that helped us basically turn taking the derivative of any polynomial into a super easy basic problem that's just really not a challenge at all. Using that power rule for derivatives makes it just so easy. So we're going to look at some examples that utilize that. That are some kind of polynomial function, polynomial models, and their derivatives. We're going to look at how they work together. So we're going to do this in 3 parts again, just like in 3.3. This is going to be a quicker section. We're just going to kind of do 3 different problems, but first I'm going to set something up just to remind us that what derivatives actually do, right? And so to start that out, first of all, right, we are in 3.4, right? And so I want to remind us about the average rate of change function that we learned back in like maybe a Math 111 or college algebra or just earlier on, right? So we say that the average rate of change of a function on the interval let's use interval notation on the interval a to b is f of b minus f of a over b minus a, right? So this is the average rate of change of this function f on the interval from b to a. So we can use that to help us out. Okay, sorry about that, guys. My allergies are being a little fun, so hopefully it won't be too chunky. So, the average rate of change of a function on the interval from a to b is just this nice, simple little difference quotient, right? Now, if we change that interval, we consider the interval from a to a plus h, we get something a little different. Not where. We get f of a plus h minus f of a over, and now we'd get a plus h minus a, which just simplifies to be h. Now you may be looking at this different quotient saying, hey, this looks a little familiar, and you're right. Right? If we take the limit as h goes to 0 of this last formula, we get the limit as h goes to 0 of f of a plus h minus f of a over h, which is equal to f prime of a. So we get this derivative at a, right? And so this is just kind of to remind us that the derivative of a function at the point A is the, instead of up there where we were talking about average rate of change, because we're going to add a singular point, is the instantaneous rate of change. Instantaneous rate of change. So this is all to go into and show and talk about how derivatives measure rate of change, right? That's kind of what they do, the way they're kind of built. The way we can use that is actually really kind of cool. And so what we're going to do are 3 parts here. It's going to be 3 different examples, utilizations of this idea. And the first one we're going to do is a very simple thing that we've already seen before, but we're going to kind of ramp it up. We're going to make it a little more complicated. We're going to add to it because that's what we like to do. We don't want to do the same thing. So what we're going to talk about is position velocity, acceleration, and the relationship between those three things. Okay, and so let's get a nice formal definition of this before we get into any sort of example. So we want to say let S of t be the position of an object at time t. Now, the first thing we want to make a note of is S of t is going to be differentiable. The reason we know it's going to be differentiable is because it's the position of this particle, this object, whatever we're talking about, right? So it's kind of where it's at. So in the sense of the real world that we live in, which is what all these examples that we're dealing with, these position functions are, we know nothing can jump, right? I mean, things can jump, but then there's still a continuous position for it, right? It doesn't instantaneously move, right? We have no teleportation abilities. So because of that, we know all these functions are continuous. And because they're all continuous, we know that they are all going to be differentiable. None of them have any sort of like absolute value, instantaneous, like jump kind of things. That's just the way the world works. So physics shows that, and everything else backs that up. So if S of t is the position of the object at time t, the velocity of the object at time t is v of t, which is just s prime of t. And the speed of the object at time t is just the absolute value of v of t. Now, this is not acceleration. The acceleration we're going to do in just a sec, but I want to talk about the difference between velocity and speed. When we're looking at this here, what we're talking about with velocity and speed is a non-directional measure of how fast something is moving, whereas velocity is like a vector. It has not only a magnitude, which is essentially the speed of the object, but it has a direction. And so when we think of driving on the freeway, right, let's say let's talk about just I-5, right? We've got I-5 southbound, I-5 northbound, right? Let's say two cars driving exactly the speed limit. So most parts of I-5, that's 65 miles per hour. So if we're on I-5, right, and we've got a car going north 65 miles an hour and a car driving south at 65 miles an hour, both their speeds are 65 miles per hour. However, when we want to talk about their velocity, we need to have their velocity in relation to some direction of travel. And so if we say let north be positive, because if we think about, looking at a map, that's up, and we typically think up is positive, down is negative. So plus down is towards California and boo California, right? I'm just kidding. If you're from California, I'm sorry. I am too. So in that case, then the northbound vehicle would have a velocity of 65, whereas the southbound vehicle would have a velocity of negative 65, because they are moving in the opposite direction of kind of what was set as positive. Now, we can't just look at something. You can't just like pop into a situation and be like, that has a velocity of negative 65, that has a velocity of positive 65. If we see two things going in opposite directions at the same rate of speed, we know that they will have equal but opposite velocities, so 65, negative 65. But that does not necessarily mean that we know which one is which without having some frame of reference that is initially given to us. So if any problem is asking you something about velocity and kind of what direction it's traveling or anything like that, know that you have to know what the frame of reference is for that first. Now, acceleration. Acceleration of the object at time t is, I'm going to do this on the next line down, is a of t, which is simply v prime of t, which is s double prime of t. So if s of t is our position vector, the velocity is the first derivative, the acceleration is the second derivative. And this gives us a nice formal definition of these three things. So very simply, we have position, which is s of t. We have velocity, which is v of t, which is just s prime of t. And we have acceleration, which is a of t, which is v prime of t, which is s double prime of t. Okay, so I'm going to pause real quick because I got to blow my nose. Sorry, guys. All right, so we now have a nice definition of position, velocity, and acceleration. So now let's look at an example that utilizes these. So the statement of the problem is very important because, as I talked about with the velocity, right, we need to understand what the frame of reference is so that we understand whether something's positive or negative, and or what that means if it's positive or negative. So let's see, let's just go ahead and give our nice little problem statement. So the particle moves along a coordinate axis and we want to say what direction. So a particle moves along a coordinate axis in a positive direction to the right. So what this tells me is if we think of, say, an axis, vertical axis or horizontal axis, right? If it's moving this direction, that is moving positively. If it's moving this direction, that is moving negatively. So that's what this statement here tells us. So this gives us that frame of reference. So this would be like inferring that northbound traffic has a positive velocity, whereas southbound traffic has a negative velocity on I-5. So that's why this is really important to understand and interpret what velocity actually is telling us here. If its position at time t is given by s of t equals t cubed minus 4t plus 2, find the velocity and acceleration at 1 second then use these to answer the following. Part A is the particle moving left to right, or right to left. And B, let me specify, there's one thing, right to left, at 1 second. And part B is at 1 second is the particle speeding up or slowing down. So, questions, question marks. All right. So, the first thing we need to do is find the velocity and acceleration at 1 second, and then we need to use that to identify whether this particle is moving from left to right or right to left. And then we need to ask, is this slowing down or speeding up? Now, this is kind of an interesting thing. This is definitely a problem where it's not an example problem that I would expect you to be able to figure out necessarily right away on your own. The first part is something that you guys should be fairly comfortable looking into, but the second part is definitely something that we haven't talked about and we'll discuss as we go through the problem. So the first thing we need to do is we know that S of t is t cubed minus 4t plus 2. So we need to find plus 2. We need to find v of t, and then we need to find a of t. Now, v of t is simply the derivative of s of t. We don't need to write down a bunch of steps and do all this crazy stuff and do anything like that. We can just simply use our rules from 3.3. We can take the derivative of each term of s of t using the power rule to do so. So the derivative of t cubed, we bring our exponent out front, we get 3t, and then we drop the exponent by 1, so from 3 it goes to 2. Our next term we have negative 4t, so the negative 4 stays. The exponent on t is 1, so that's why we have negative 4 times 1, that's why the negative 4 stayed. If this was negative 4t squared, then we would end up with negative 8, but because it's negative 4t, the negative 4 just hangs out. And then drop the exponent down 1 goes to 0, t to the 0 is 1, so it's just gone. And constants, derivative of constant is 0, so that's it, we're done. There's the derivative of s of t. Now for the derivative of a of t, we just take the derivative of v of t. So again, just piece by piece. So we have 3t squared. So taking the derivative of that using the power rule means that I take 2 times 3, giving me 6t, and I drop my exponent from 2 down to 1, so we're good. The derivative of negative 4 is 0, so that's it, we're done. We have our position. We have our velocity. We have our acceleration. So we now just need to evaluate what's v of 1 and what's a of 1. So v of 1 is 3 times 1 squared minus 4. 1 squared is 1, 1 times 3 is 3, 3 minus 4 is negative 1. And a of 1 is 6 times 1, which is 6. Now I don't care where the particle is at this moment in time. What I'm concerned with is how it's changing. And so we want to look at the velocity and the acceleration. Now, a quick note, this problem here, right, if we go back to our initial statement of the problem, we said that a particle moves along a coordinate axis in a positive direction to the right. There's a couple of things. First of all, the reason why we talk about particles is because they are considered infinitesimally small. They have kind of a zero width essentially, so we don't have to worry about like an object. Like it's definitely different if a needle is moving along versus a big wooden branch, right? Things like friction and play into all of those things, and we're just wanting some really pure mathematical practice here, so we're kind of using situations that can ignore all of those components. Then the other reason why it's moving along a coordinate axis and not just moving along, say, the line y equals x, is because moving along the coordinate axis, we can limit ourselves to considering only a single value. Because if I know it's moving along, let's say, the x-axis, if I say it's at 3, I can go, okay, well, that's at 3 on the x-axis. But if it's moving along a y equals x or y equals 5x or some other line, some other curve, we have to create a function, a position function that is actually a two-dimensional position function, because it needs to tell us not just where it's at on the x, but also on the y, so we know exactly where it's at. And that's why for these problems where we're trying to be simple and keep things easy and focus on our calculus skills, we do a particle moving along a coordinate axis. So just want to bring that up and point that out. So if you're wondering, like, well, what about wind and gravity and all these things? Particles are too small. We're not worried about it. It's negligible. So for part A, is the particle moving from left to right or right to left? Well, if you remember, the problem initially stated that the particle was moving positive direction to the right. So that means this way is positive. This way is negative. So since v of 1 is -1, right? So v of 1 is less than 0. The particle is moving from the right to the left. And that's it. Right? It is moving against the original flow that we had defined in the problem because its velocity is negative. Pretty easy. Now, B, this one is a little bit trickier in a way. It doesn't matter what direction is considered positive or negative necessarily. It just matters the relationship between the velocity and the acceleration here, which is really kind of strange. But it's the way it works, because acceleration is still given that kind of initial value or that initial direction. And so here we'd say, since v of 1 is less than 0 and a of 1, which if you recall is 6, is greater than 0, they're acting in opposite directions. So we can almost think of the acceleration as a force acting on this object, which is not exactly correct, but if you want to, it's kind of a better way to kind of visualize, because the really true theoretical way of kind of like thinking of this is honestly kind of strange. And so a really simple way to think of it is the acceleration is almost like a force acting on this particle. So if the particle is moving from the right to the left, but the force, the acceleration on it, is moving from the left to the right, right, in the positive direction, those are moving against each other, right? So they're going to minimize each other's effects. So because they are opposite, the particle is slowing down. Right, and that may be slightly counterintuitive if you're thinking, oh, hey, a of 1 is greater than 0, right? The acceleration is positive, so this thing is speeding up. But it is actually, it's positive in relation to the initial, into the positive direction of travel, or in this case here, to the right. And so because that's opposite of the direction of travel of the particle at this moment, it is actually slowing down. These are kind of working against each other is what's happening. So I hope that made sense. I hope that you guys are kind of feeling this. And that's it for part 1.